What's up, guys? It's still me, the great teacher. I forgot to make an intro and outro for this video. Let's just jump right into the lesson, homies.
So for this concept, we're going to use GeoGebra in order for us to understand the properties of tangents and the theorems related to it. So first off, what I'm using here is GeoGebra Classic. You can also use the concept of, the application using your tablets, your phones, your iPads, even on the website. So we're using GeoGebra Classic because this one is the one that will best fit the concept of circles and the theorems related to them. So I will put all of my concepts or images in the first quadrant so that you guys will be able to see it clearly. So first off, for us to understand the concept of tangents, let's first have a circle. So if you click the circle option, you have a lot of options there. Let's pick our choices. So you'll pick circle with center to a point so that we'll be able to start with our first concept, which is the point of tangency. So first off, click anywhere, and then you'll be able to have not only a point but also the center. So the circle is formed here, and the good thing about this one is you can already see the equation of a circle in this kind of example. But we're not focusing on that yet. What we're focusing is on tangents. So we go to the move a little bit, and what we're going to do next is we're going to have the tangent. So we click this option right here and go to the tangents. So for the tangents, we click the point B and the circle. So point B there stands as the point of tangency of this given example. So this one will be something that we'll be doing all throughout this video, this tutorial. What we're going to do is we're going to form segments. So in order for us to do that, we're going to maximize this image. So say from C to D. So you might be wondering, why am I forming a segment here? So that we can hide the tangent line. Instead of having a tangent line, let's have a tangent segment. So this tangent segment right here is, as you can see, tangent to the circle, and they meet at the point of tangency, which is B. So in this case, the first thing that we will discuss is the tangent theorem, where all we have to do first is to draw a radius. So from A to B, that's a radius. Now, the concept in here that you're seeing is that the radius is connected to the point of tangency, and basically that states that the radius is indeed connected to the tangent segment, because the first thing that we have to prove or show here is the tangent theorem, which states that a tangent to a circle is perpendicular to the radius drawn at the point of tangency. The reason why we're using GeoGebra is you can actually check if this is indeed true. So they have here the angle option, so we click this one. So from A, B, D, as you can see, it's 90 degrees. And that's our first theorem. As quick as that. So you can maximize the use of GeoGebra for this one. So let's go and make another circle for our other theorems or corollaries related to the tangent theorem. So let's make another circle. So circle with center to a point, go here and here. So what I will do now is I will have an external point, meaning a point outside the circle. So I'll have point G right there. So what I will do now is go to tangents again, click the circle, and instead of clicking point F, I'm clicking the external point G. And as you can notice, we have here two intersecting segments, and these lines. So we want to form segments again, so we click the segment option. We have there point H as our intersection, point of tangency to G. So here also I and G, so we have those segments. Let's hide the lines, and we now have this. So in this case, you have two tangent segments, tangent to the given circle E, and they are both connected to the external point G. For corollary number 1, it simply states that these two tangent segments from a common external point should be congruent. So for us to check that, let's see their distance from H to G and I to G. As you can see, they're both 4.9, so it's indeed correct. You can move these things a little bit if you find it confusing or distracting. maximize the move option. And the beautiful thing here is that you can actually move the point. You can move it to the point that you will be able to see that the tangent theorem is indeed true. So again, the tangent theorem, corollary number one. For corollary number one, it simply states that HG is congruent to IG. It's our corollary number one. So that's corollary number one, stating that again, two tangent segments from a common external point are congruent. So let's use the other corollaries related to this tangent theorem using the same image. So now let's have another segment, this time connecting the center and the external point. So as you can see, this segment that we created from E to G meets the angles formed at G, separates them, meaning we have two angles now formed at G because of this said segment. And under corollary 2, it states that two tangent segments from a common external point determine an angle that is bisected by the segment formed from the external point to the center of the circle. So if you want to verify that, you can go to the measurements again. So EGH, wait, that's wrong, sorry. HGE, that's 26.75. EGI should also be 26.75, and it is indeed true. So that's corollary number 2, stating that again, the angles are bisected in this case. So let me just write that down there. So for corollary number 2, we have angle HGE congruent to angle IG. And again, if you want to move it out a little bit, it's still true. It doesn't change. Now, the thing that we're going to do next is the continuation of corollary number 2. In corollary number 2, we draw a segment from the center to the external point. So what if now we draw the radius or the radii? HE, sorry, that's wrong. It should be segment H to E and E to I. So the purpose of this is basically the continuation of all the corollaries stated, corollaries 1 and 2, and then at the same time the tangent theorem. We know that HE, the radius, when it meets the point of tangency, there will be perpendicularity in there. And if you want to verify that, again, sorry, not distance but angle, so EHG 90, EIG, oops, wrong, other way around, GI 90. Again, this is an application of tangent theorem. And now, what are we trying to say here? Not only do we have here the concepts or the tangent theorems and the corollaries together, but also we were able to form an image. We have here two right triangles. So it's here and here. There's two right triangles, okay? So what I want you to understand is that, again, this is the image we were able to form. And the next thing that we're going to do is as simple as identifying what do these two triangles have other than the fact that they're both right triangles. Actually, they're going to be congruent also. So if you're wondering about that, we stated in corollary 1 that HG and IG are congruent. But also, HE should be congruent to IE. Why? Because again, they are radius, the radii of the circle. They have the same measurement. Now, if you look at GE, from point G to E, this is the part where both triangles meet. They share the same side. So we know for a fact that GE is congruent to GE thanks to the reflexive property. Meaning, not only are these two triangles right triangles, but they are also congruent by SSS. side, side, side. This is going to be SSS. So meaning, we can say that our conclusion for this lesson is that if you have an image similar to this, we can say that we have triangle GHE congruent triangle GIE. Not only are they congruent, they're also two right triangles. So that's it for this one. But now let's try to actually apply the skill that we learned here using examples or an example. So let's go to that one. So let's say that we have this example right here. It's similar to what we just did earlier. So we have AB and AC tangent segments. So AB is 12. So let's write that here. AB is 12. AD 13. BAD is 24. So as stated in Corollary 1, AB and AC should be congruent. So this is 12. BAD and DAC should also be congruent under Corollary 2 because they were bisected by segment AD. Other than that, what else can we find here? So AC is already at 12. BD, how will you get BD? That's a question. And again, this is an application of what we have applied last time, earlier. There should be right angles here. So we're actually going to go back a little to your grade 9 lessons, which is the concept of the Pythagorean theorem, in order for us to answer this one. So why are we using Pythagorean in this example? Pita. How do you spell Pythagorean? Oh God, I'm so bad at spelling. I might be wrong with the spelling. Please forgive me. I'm bad at it. So the Pythagorean theorem states that c squared is equal to a squared plus b squared, or the other way around. And the reason why we're using this is in order for us to find the measurement of the radius, BD and CD. So how do we do that? We know that already in here, we can have either this triangle or the other one. Either way, it's going to be the same. So 13 is going to be the hypotenuse, or C, because it's opposite to the right angle. So we have 13 raised to 2. Our legs, A and B, could be either way. So either AB or BD. So I'll have 12 instead here. And the B is still missing. So because that's the BD, the one that we're looking for. 13 squared is 169. 12 squared is 144 plus B squared. So transpose 144. Continuing here, we're going to have 169 minus 144 equal to B squared. So 25 is equal to B squared. Get the square root of this and you'll get 5 is equal to B. So the radius is equal to 5. So BD is 5. CD is also 5. As quick as that. Now we have DBA. DBA is 90 under tangent theorem. CAD is 24 under corollary number 2. Now BAC is 48 because we add BAD and BAC. We had that lesson before when you have adjacent angles that share the same point. You can add them. So that's the example number 1 that we have here. As quick as that. You don't really have to make this example complicated. Now, what if we apply these concepts now in relation to circles inscribed in an image? So before we go to the next one, let's go back to our dear GeoGebra. So let's go to a different space here instead. Oh, I'm sorry. So now, it's important that we also understand the concept of not just the tangents and the circle, but also what if we have, let's say, what we call as internally tangents or externally tangents, or internal tangents and external tangents. So first off, we will start with what we call as kinds of circles with kinds of common tangents for circles. So let's say we have here internal tangents. Actually, with this image that we're going to form in GeoGebra, it's going to show both already, both internal tangents and external tangents. So basically, let's say that we have two circles. Let's have two circles. So we want to show common tangents for these two circles. So we go to tangents again, click both circles, and look at what you can see. These things here we're seeing is actually the internal tangents and the external tangents already. So to better understand this, I'll just write the concept here. Don't worry, I'll show the slides. What do you mean slides? Again. I cannot write for some weird reason. I don't know why. But yeah. Now I can write. This one is so goofy. So we're talking about here internal and external tangents. So basically, in this image itself, we have both. So to put this into perspective, we can say that we have internal tangents when we're talking about these tangents in particular. Wait. Yeah. So these are called internal tangents. Again, these are called internal tangents because if you connect the segment from J to L, meaning the centers J and L, if you connect them, it will intersect both tangents. So that's why they're called internal tangents. While for external, so basically it's the other way around. External will not meet said tangents. So as you can see here, these two tangents, whether segments or lines, they do not intersect with the segment formed when you connect both centers. As easy as that. So that's internal tangents and external tangents. But what if now we have internally tangent and externally tangent? This one is better shown with GeoGebra 2, but it's kind of complicated to do, so I'll challenge you to do that. But it's basically as simple as this. Earlier, there's a correction. We discussed there the concept of common tangents for circles. But this time around, it's still similar to it, but it's now more about tangent circles, meaning circles sharing the same point of tangency. Internally tangent, based on the image itself, they share the same point of tangency here, but the circle is inside, the smaller one. As for externally tangent, they share the point of tangency, but they're not, the smaller one is not inside the bigger one. So excuse me. So that's basically the difference between the two. You don't have to make that super complicated. So the reason why I'm showing this is, as you can see, the images wherein you can see a circle inside another circle. That kind of concept is actually what we call as having polygons inscribed inside another one. So as stated here, if every vertex of a polygon is a point on a circle, the polygon is inscribed in the circle, and the circle is circumscribed about the polygon. It could also work both ways, where we have, when a polygon is circumscribed about the circle, each side is tangent segment to the circle, and the circle is inscribed in the polygon. This one, we can show this to GeoGebra again. We can try that one. So let's draw another circle. This one is actually easier to understand with this. So what we have to do here is we have to identify points. So let's have a point here, point here. Sorry. Then I need an external point here. So what I will do is I'll form tangents here. Tangents with point R to Q. Oh yeah, I don't know how to do that. Sorry. Yeah, I don't need the points. I just need one, I think. Yeah, I need one only. Wait, what? Wait. Okay. Yeah, I just need one. Tangents. Then I'll add another point here. Then tangent again. And as you can see, we were able to form something already. So I'll go with the segments so that we can hide the lines. And as you can see, the circle is inside a triangle. And with this, it's actually easy to get the measurements because it's application of the corollary 1, if you want to point that out. So this should be 3.93 also. Wow. Oh, wait. That's not the point of tangency. Sorry. The O is not the point of tangency. U is. Okay. So, sorry, O is not the point of tangency, guys. U and S, R and S, 3.93. Nope. Not that one. U and P should be congruent to that one. Wait. Why am I clicking the wrong things? Whoa, I need the point of tangency here. Okay. Nope. Okay, point of tangency, measurement, V to P, T to V, T to up. Okay, so you can see, just applying the tangent theorem here and the corollary should be able to have a lot of things in terms of the measurements. So let's use it using an example. So we have here FGH, circumscribed circle P. We have a proportion saying that GK, HL, and FJ is 5:2:3, and the perimeter of the triangle is 100. So all we have to do here first is understand what this given ratio means. Simply, it implies that GK corresponds to 5, HL corresponds to 2, and FJ corresponds to 3. Now, if you remember your lessons with ratios and we have values like this, we know that it's not the actual measurement. Instead, it's the ratio of the measurements. Hence, we can say that this is 5x, 2x, and 3x. So if you put that here, GK is 5x, GK is from here to here, not the entire thing, by the way. 2x for HL, 3x for FJ. So that ratio is not enough for us to identify their measurements, even with the help of the perimeter, because we need to apply first corollary number 1 here. So corollary number 1 from our tangent theorems is that when you have a circle, an external point, if you connect that, these should be congruent. That's why it was stated earlier in the concept that we have a circle inside a figure, inscribed in a figure. Basically, those will be tangent to it. So in this case, GJ or GF, that entire thing is tangent to this circle. So it applies the concept of corollary 1. So if GK is 5x, GJ should also be 5x. As simple as that. Oops, not that one. Next, KH and LH should have the same measurement also. This should be 2x. And this one should also be 3x. As quick as that. And then, since it's about perimeter, let's add all of these measurements. 5x plus 5x is 10x. Plus 3x plus 3x plus 2x plus 2x. It's going to give us 20x. And it should be equal to the perimeter, which is 100. Divide both sides by 20. Your x is going to be equal to 5. As quick as that. So in this case, we can say that this is 25, 25. This is 10, 10, 15, 15. And if you add all of those things, those measurements will give us 100. Now, it says that measure of F is 62. That means this angle is 62. Now, to better understand this, in order to really get the other measurements, the one that is being asked on the left side, you have to understand the concept that we have discussed here. So let's separate this image right here, the FGL. Let's draw that one. This is F, this is J, this is L. F is 62. We know that F, J, and FL are congruent. They're both 15. So JL, we don't know the measurement of it, but we don't have to look for it anyway. But what I want you to understand here is the concept of isosceles triangles. Not only are two pairs congruent in terms of their sides, but also the angles opposite to them, meaning J and L are congruent. So to get their values, we know that the interior angle, the sum of the interior angles of a triangle is 180 degrees. So we subtract 62 from that, from 180. So you will get 118. And since J and L are congruent, this 118 should be divided by 2. And the answer will be 59. Diba? Fast forward, 59. So this one will be 59 degrees. This one will be 59 degrees. Again, the importance of this, or the reason behind this, is because they are isosceles triangles. Isosceles means that two sides are congruent, making also two angles being congruent, but the sides is the important part. So GKP right here, what kind of triangle would that be? That's going to be right, by the way. This is a right triangle because tangent theorem. What else? The isosceles triangles are FJL, GJK, and lastly we have KHL. FJL, we were able to get it. It's going to be 59 degrees for 59. So that's it. Basically, we don't have to overcomplicate it. We just apply the concepts we have learned in terms of the theorems and corollaries related to tangents. That's it for this one.
Thank you for listening. I hope you learned nothing. Joke. In case you don't see me soon, good morning, good afternoon, good evening, and good night. Peace out. Respect.